Thank you very much for your introduction. Hello. As Chris said, I will present you the results of my master thesis I did for the National School of Arts of La Cambre 2 years ago, which treated Pemulen gels. I will start by defining the context and the goals of this study. As you surely know, Pemulen is a polyacrylic acid polyacrylate ester block copolymer used to formulate cleaning gels. The macromolecule has a hydrophilic and a lipophilic portion that gives the polymer an emulsifying ability to create oil-in-water emulsions. To formulate Pemulen gels, we need to neutralize the copolymer with an alkali in an aqueous environment. Generally, trethionamine is the chosen alkali. However, this alkali has been considered risky for pictorial layers because it has a high penetration and a high retention rate, being a potential source of residues that can swell and lixiviate pictorial layers. Therefore, we decided to evaluate the use of other alkali in order to replace eventually trethionamine. We choose for that 3 other organic alkali, etomine C25, tris, and bistris. When the polyacrylic acid is neutralized by amines, which are weak alkali, the resulting species are partially dissociated in water and exist in both ionic and neutral form, as you can see on the picture. If present in sufficient amounts, free amine can form methyl-like structures that can offer supplementary emulsifying, solvent, surfactant, and chelating actions that could be very useful for specific cleaning tasks. But viscose amines, as trethionamine or etomine, could leave residues. We also choose to compare inorganic alkalis, sodium, potassium, and ammonia hydroxide. Sodium and potassium hydroxide are strong bases, dissociating totally in an aqueous environment. They exist as highly mobile and reactive ions that may migrate through pictorial layers during aqueous cleaning. Under certain conditions, these ions could produce oil hydrolysis or induce some pigment degradations and form salts. But they allow to reduce the risks of leaving residues, especially ammonia hydroxide, which is extremely volatile. So we decided to compare all these bases in an experimental way. And for that, our goals were first to evaluate the alkali volume necessary to neutralize Pemulen hydrogels. Actually, using the minimal amount of base could limit some of the risks for pictorial layers and reduce potential residues, allowing to establish safer recipes. Then we choose to analyze the gel pH homogeneity and stability in order to observe the capacity of Pemulen to contain the bases, especially those with a high volatility as ammonia hydroxide. After, we decided to study the rheological behavior of the gels depending on the alkali, since the viscosity influences several gels' properties. Also, we studied the emulsion capacity of the Pemulen gels, depending on the base used, and on the gel pH. Finally, we wanted to know if we could observe gel residues depending on the alkali used. So, concerning the alkali volume, the minimal alkali volume necessary to neutralize an identical quantity of Pemulen was determined thanks to titration curves, using a particular pH meter adapted to semisolids and non-polar substance, which was calibrated systematically before and after each titration. As shown in this table, the final alkali molar concentration required to neutralize 1 gram of Pemulen is similar for most bases and is extremely low, about 0.1 molar. We can see that surprisingly the etomine was the lowest concentration base in the Pemulen gels, and the bistris the highest. This is encouraging in terms of residue and other possible risks. Moreover, these minimal volumes were found to be generally lower than those reported in the scientific literature. For analyzing the gel pH homogeneity and stability depending on the base, two series of hydrogels were prepared and measured with the same conditions and materials used in the precedent experiment. We performed the pH measurements on 3 different frequencies: every hour for 5 hours in a single day, then once per day for 1 week, and finally once after a month. You can see in this graphic the vertical bars showing the standard deviations after the measurements performed every hour. These deviations revealed local heterogeneities in the entangled structure of the gels. The gel containing etomine presented the largest pH variations, which might be due to the large size of etomine molecules, which reduce its diffusion into the Pemulen network, compromising its homogeneous repartition in the matrix of the gel. In this graphic, the horizontal blue bars shows the 7-day average pH and the red bars shows the standard deviation. The horizontal green bars indicate the pH after 1 month. We can see that the different gels show only slightly pH variations after 1 week and 1 month. The most important variations were found when using ammonia hydroxide. However, this cannot be attributed to its volatilization since the pH value did not gradually decrease. Further research is needed to explain these trends. But in a practical point of view, we can advise to perform pH measurements and to stir the gels before using them in order to promote homogeneous repartition of the base in the polymeric network and to ensure a better control of the cleaning intervention and the pH. Concerning the rheological behavior, in order to analyze the viscosity of Pemulen gels, depending on the base, we prepared hydrogels with each base using the same materials already mentioned and using a rotational cylinder rheometer. We could observe that the rheological behavior is very similar for all the alkalis. All the gels have high viscosity when at rest, but the viscosity decreased when they are churned. Gels containing etomine possessed the lowest viscosity at rest, showing the lowest vertical and horizontal hold. This should be considered, for example, for specific cleaning tasks as a vertical cleaning. To analyze the emulsifying capacity of Pemulen gels, depending on the base, we prepared 2 series of Pemulen hydrogels, one with pH 5, the other with pH 7, and afterwards little volumes of white spirit were slowly added. We could observe that both mineral and organic bases have very similar emulsion capacity. We could reach up to 48 to 50% of white spirit for pH 5 gels and 45 to 46% for neutral gels. The only significant difference was found with etomine, which allowed to incorporate up to 88% of white spirit. Therefore, etomine acts as co-surfactant, enlarging Pemulen emulsion capacity and creating even water-in-oil emulsions. Finally, in order to find gel residues, we observed oil in canvas samples cleaned with gels containing a mineral base and 2 organic bases with a scanning electron microscope. For each chosen alkali, 2 Pemulen hydrogel removal methods were observed. First, a dry removal only, and then a dry removal followed by a water rinse. However, none of the observations allowed us to confirm the presence or the absence of gel residues on the samples, so we couldn't conclude that much. In conclusion, molar concentrations required to neutralize 1 gram of Pemulen are similar and very low with all bases. Also, the gels seem stable over long time periods with all the bases, but local heterogeneities can be found especially with etomine and ammonia hydroxide gels. We saw the rheological behavior is very similar for all the alkalis, but gels containing etomine possess the lowest viscosity at rest. Then, stable emulsions can be produced with both mineral and organic bases, but especially with etomine, which enlarge a lot the emulsion capacity. Finally, further research is required to compare gel residues depending on the alkali used. And it will be nice to continue this research, maybe you. So, we can definitely conclude that alkali studied can easily replace tretylonamine in Pemulen formulations. Nonetheless, further studies on the chemical interactions and of the alkali studied and the materials found in artworks should be performed. Finally, we believe that each alkali could be used for a particular cleaning task depending on the requirements of the cleaning intervention. You will find on my paper a table showing the criteria and the alkali we propose for different cleaning tasks. For example, eventually, if we want to minimize residues, we can choose ammonia hydroxide. But if we want to increase the Pemulen emulsifying capacity, we could prefer etomine. Thank you very much for your attention.